Isotopes can be used from everything from radiocarbon dating to determine how old a fossil is. They can be used in nuclear reactors. They can be used in nuclear medicine in case a doctor suspects somebody is sick and they want to determine exactly what's wrong with them. They can use different types of isotopes. So let's talk about what isotopes are, and let's talk about how to write isotope notation. So first off, an isotope is going to be an atom that has the same atomic number, but it has a different atomic mass. Now, we have to remember that the atomic number determines who the atom is. For example, and you should remember from our last video, let's say if we have sodium, sodium has an atomic number of 11. And that tells us the number of protons and the number of electrons in a neutral atom of sodium. Always tells us the number of protons, though. And we said that that sodium, in general, had an atomic mass 22.99 AMUs. There's our average atomic mass. Now, what we're saying with isotopes is that an isotope can have different atomic masses, but they have the same atomic number. And where that differing atomic mass comes from is different number of neutrons. So if we change the number of neutrons, we change the atomic mass, but as long as we keep the atomic number the same, we still are the same exact atom. So let's talk about, first off, how to write isotope notation, and then we're going to talk about how to distinguish between isotopes. Okay, so how to write isotope notation. So what we have here is I have shown 3 different isotopes. We have carbon-12, carbon-13, and carbon-14. You notice that all of them are carbon. They're all carbon. So if we look on the periodic table, and I'm going to kind of draw this over here, and you should have your periodic table out that I gave you. If we look on the periodic table, carbon has an atomic number of 6. So that's what makes it carbon, 6 protons. But each of these have different atomic masses, and so these values here are atomic mass. And so let's talk about what's going on here. For isotope notation, then we'll talk about the difference between each one of them. So if we're going to write isotope notation, what we want to do first is we're going to write down the symbol. So each of these have the symbol of C. That's what makes them, well, one of the reasons why they're carbon. The next thing we're going to do for isotope notation is we're going to write in the atomic mass. And the atomic mass, like I said, was listed here, was listed here, and was listed here. And we're going to put that right here, 14. Oh, I'm sorry. Let's put a 12 there because this is the atomic mass of carbon on this one. So the 12 is going there. We're going to put the 13 there, and we're going to put the 14 there. So this top number is going to be our atomic mass. Now the bottom number that we're going to put a number here, here, and here is going to be our atomic number. Now again, when we look on the periodic table at carbon, the atomic number is 6. So we're going to put 6 here, a 6 there, and also a 6 there. And that's how we write isotope notation. So this is isotope notation for carbon-12, this is isotope notation for carbon-13, and this is isotope notation for carbon-14. We just basically take what it looks like on the periodic table with the atomic number on top, and we sort of flip it over. Okay. Now, this allows us to do a couple of things. One, it allows us to easily calculate the number of protons, electrons, and neutrons in each of these isotopes. So let's go ahead and write this down. Proton, electron, and neutron in each of these isotopes. Okay, so let's walk you through this first one here. So, as we know, the atomic number, which is listed right here, atomic number 6, tells us the number of protons in a neutral atom, or actually in any atom. Now, because this is a neutral atom, we're assuming it's neutral, it's also the number of electrons. And if we subtract the mass number, or the atomic mass, from 6, we get the number of neutrons. Okay, so there we go. Let's do the next one. Now, on the next one, for carbon-13, again, the atomic number is 6, so we will say that it has 6 protons, and assuming it's a neutral atom, 6 electrons, and then we subtract 6 from 13, and we get the number 7 for the number of neutrons. So that tells you the difference there in carbon 13 between carbon 12. It's basically the number of neutrons. That's what we said previously. Now, you could pause the video right now and do the last one by yourself. Why don't you do that? Pause the video and do the last one by yourself. And then when you're done, you can come back and check and see if you got it all right. Okay, hopefully you pause the video and you're going to do this one by yourself. So let's calculate the number of protons. Again, atomic number is 6. The number of electrons is 6. And then we're going to take 6 from 14, and that's going to give us the number of neutrons as 8. Number of neutrons is 8. Okay, so that is how we do isotope notation, and that also tells us the important difference between isotopes of the same atom. They're going to be the same atom because they have the same number of protons, so they have the same symbol, but they are going to have different number of neutrons. That's what gives them a different atomic mass. Remember, the neutron contributes 1 AMU to the relative mass of each atom. Let's look at this sample question. It says, how are the isotopes of iodine-123 and iodine-124 similar? Okay, so we're looking for similarities between these guys. And then we're looking for how are they different. So kind of annotate this here real quickly, make sure I answer both of those questions, the similarity and the difference. If you think you've got this and you want to pause the video right now, go ahead and pause the video right now and see if you can work this out. See if you can come up with the same similarities and differences that I come up with. Okay, we're back now. So first thing I'm going to do is I'm going to look up on my periodic table, and I'm going to look up what iodine is all about on the periodic table. And we'll identify a couple things. So first on we have iodine. Okay, and iodine has an atomic number of 53 from our periodic table, and it has an average atomic mass of 126.90. Okay, so basically what we're saying here is let's go ahead and write the isotope notation for both of these. So we have I-123 and we have I-124. Okay, now remember when we put the number down here, that's going to be our atomic number, so it's going to be 53 on both. 53, there we go. I'm just going to erase this line off right here and right there. Okay, so now we have our two isotope notations written, and so let's talk about first off our similarities. How are these two similar? Well, the first thing you should be able to identify as them being similar is they are both iodine. That's one thing. And we could say also they both have 53 protons because the atomic number is 53. We could also say both have an atomic number equal to 53. And that's kind of obvious. We could also say that they both have 53 electrons in a neutral atom. And those are our similarities there. Now let's talk about how they're different. Differences. Okay, so the differences, we could say that they have different atomic masses. So you notice up here that the atomic mass of this iodine is greater than the atomic mass of this iodine. So they have different atomic masses. Let's see, what else is different about them? Well, we can calculate the number of neutrons, and so they have different number of neutrons. Remember, if we're going to calculate the number of neutrons, we subtract the atomic number, which is 53, from the atomic mass, which is 123. So on this one, this iodine 123, so we have iodine 123. This guy has 70 neutrons. And iodine 124 has 71 neutrons. So they have different atomic masses. They have different number of neutrons. Okay, and those are the differences. So similarities and differences. And as we get more into isotope and isotope notations, and into nuclear chemistry in the future, you're going to see how these isotopes really come into play with some of the things I talked about before, like nuclear medicine, as well as carbon-14 dating and things like that.